Okay, so having seen that elementary lemma in the last video, which allows us to perform some easy calculations in a vector space, let us move ahead. Let V be a vector space over some field F and W be a subspace of V. Considering V and W as merely abelian groups under addition, we can form the quotient group V by W. So we know that every vector space is an abelian group under an operation which we usually call addition. So V is an abelian group under addition, and W being a subspace of V besides other things is also an abelian group under that same operation restricted on it. In other words, W is a subgroup of V under that addition. And since our original group V is abelian, so W is automatically normal in V. So we can form the quotient group. Moreover, this quotient group, these are things we already know from group theory. The quotient group itself is abelian. So we have now got an abelian group. Now can we define a multiplication by scalars in this group or on this set? That is, can we define an operation where we multiply an element from here by a field element from here, so that we again get an element here, and so that V by W is turned into a vector space over F? The answer is yes, we can, and that's what we are going to do now. For any field element alpha and any element in V by W. V by W has, what are the elements in V by W? They are cosets of W in V. But we are not going to write them as VW because our operation is addition, so we will write V plus W. And we define like this. This product is defined to be equal to alpha V plus W. Let us see what this really means. Alpha V plus W, what is it? See, since this V has to come from capital V, because this is supposed to be a coset of W in V. So the element that is being used to form this coset, that element should come from the original group V. So this small v is in the vector space V. Sometimes we will call this capital V a group, sometimes we will call it a vector space. You have to understand that when we say it's a group, it's under that addition that it has. Okay, so V is an element in this vector space and alpha is a scalar. So this alpha V is the ordinary multiplication of vectors by scalars that we have in the vector space V. So this alpha V is again an element in V, that is again a vector in capital V, and so this is a coset of W in V, and that is why this belongs to V by W. But the thing is that we still have to show that this operation is well defined. Just the results of the operation being in V by W is not enough to say that it's well defined. For that we have to show that if we have the same scalar, that is if we have two scalars, say alpha 1 and alpha 2, which are equal, and two vectors or two elements here, say V1 plus W and V2 plus W, which are also equal, then the products should give us the same element. Let us now show, or in fact there is no need to write these things. We can start like this. Let alpha and beta belong to F and V1 plus W and V2 plus W belong to V by W such that alpha is equal to beta and V1 plus W is equal to V2 plus W. Okay, now these two cosets are equal. That implies the vector V1 minus V2 belongs to W, which is again from group theory, where we know that, say we have a group G and there is a subgroup H, and suppose G1 and G2 are two elements in G, then the two cosets, and suppose also for the sake of matching the situation with this one, that the group is abelian, so that H is a normal subgroup, because all those things are there. Then the left coset G1H is equal to the left coset G2H. That implies G1 G2 inverse belongs to H. Now here our operation is addition, so in place of G1 G2 inverse we will write, so here we have V1 plus W equal to V2 plus W. So in place of V1 V2 inverse we will have V1 minus V2, which is just V1 plus inverse of V2, which is minus V2. This belongs to W. Okay, so that's what we are now going to use, and that is coming from group theory. So we will just simply write, this implies, or then alpha is equal to beta and this. Sorry. V1 minus V2 belongs to W. Okay. Now we are going to use the fact that W is a subspace. Now since W is a subspace of V, we have alpha times V1 minus V2 belonging to W, because V1 minus V2 is in W. So if you multiply that by the scalar alpha, that product will also be in W. But this is equal to, now use that lemma that we saw in the last video to carry out this multiplication, alpha V1 minus alpha V2. Actually, if we just simply write it directly like this, then it may be somewhat confusing. So let us see the intermediate steps. The real meaning of V1 minus V2 is V1 plus minus V2. Now since these are vectors and this is a scalar, so from one of those four vector space axioms, this will be equal to alpha V1 plus alpha times minus V2. Okay. Now this is where you use lemma 411. Lemma 411 says that minus V2 is minus 1 times V2. Again you use one of the four vector space axioms to bring these two field elements together. Alpha times minus 1 V2, which is just this thing. Alpha times beta V is equal to alpha beta V, that axiom. Okay, where alpha and beta are scalars and V is a vector. Now multiplication in the field is commutative, so we can change the order of this product, order of the elements. So we can write minus 1 times alpha V2. Again use the third axiom. Then again, just like in place of minus V2 we have written minus 1 times V2, we use that same thing here and write alpha V1 plus minus of the vector alpha V2. And this of course is written as alpha V1 minus alpha V2. So because this itself belongs to W, so this will also belong to W. And hence alpha V1 plus W is equal to alpha V2 plus W, because W is a subgroup under addition, subgroup of V. So this thing, just like this implies this, this also implies this. They are equivalent. For alpha V1 plus W, this coset is equal to that coset. Thus, we finally have alpha times V1 plus W, which by the definition of this product is alpha V1 plus W. which we have just now shown is equal to alpha v2 plus w, but alpha is also equal to beta, so here you can write beta v2 plus w, and then you use this definition again and write this product or this coset as this. So you see that if our scalars are the same and cosets are the same, then the products also are the same. Thus, the above operation, you know which operation we are talking about, this one. Is well defined. Okay, so fine, we have gotten a well defined operation. Now we have to verify those 4 vector space axioms in V by W with respect to the addition we have here and the multiplication by scalar we have defined. Next, let alpha and we already took alpha. It does not matter because they are just variables. These are any field elements and these are cosets. Note that alpha times if we add these two things, and this becomes equal to, you should understand that this addition is what? Okay, what is this addition? This addition is the binary operation in the group V by W, which is coming from group theory when we are considering V as an additive group, W as a subgroup, and getting this quotient. It's that operation in the quotient, which is addition of two cosets. And according to the definition of that operation, this addition is U plus V plus W. Okay, so this addition has been carried out in the group V by W. Now we apply this operation. So according to this definition, this is alpha times U plus V plus W. Now use the fact that V itself is a vector space and U, V, these are elements of capital V, and alpha is alpha is coming from the underlying field of scalars. So this part can be written as alpha U plus alpha V plus W, and that is coming from axiom 1 in the vector space capital V. Again, you use the binary operation we have here in V by W in that group. According to that operation, so whatever plus we have done here we are going to do the opposite. This is the sum of these two cosets. Okay, and then again we use this definition. So this will be equal to alpha times u plus w plus alpha times v plus w. So you see that axiom 1 for a vector space has been shown in v by w, because alpha times one vector plus another vector is equal to alpha times that one vector plus alpha times that another vector. So this is only one of the things. Then we one by one we show that the other axioms are also satisfied. Then alpha plus beta times u plus w. So by the definition of multiplication by a scalar, this is alpha plus beta times u plus w, and this is equal to, here you use the usual vector space axiom, the second one I think, alpha u plus beta u plus w. Again by the definition of addition in the quotient group, this is alpha u plus w plus beta u plus w, which is equal to alpha times u plus w plus beta times u plus w. So the second axiom has also been verified to be true. This of course again is coming from our definition of the second operation in v by w. Then alpha beta u plus w, this is equal to alpha beta u plus w. And this in the vector space capital V is equal to alpha times beta u. So this coset is equal to this. Now apply the definition of second operation two times. So first, once you apply it, you get this product. Okay, alpha times the coset beta u plus w. Once again you apply it, you get this. So that is, this entire thing is just like this thing, alpha beta times u equal to alpha times beta u, alpha beta times coset equal to alpha times beta times that coset, and finally 1 times u plus w, where 1 is the unit element in the field, is by definition 1u plus w, but in the vector space capital V, 1u is u, so we get u plus w itself. So all the axioms have been verified for u by w. Thus we have the following. So the conclusion of all these things we are going to write as a lemma. Thus we have the following result. This is lemma 412. If V is a vector space, over a field F, and if W is a subspace of F. Then V by W is a vector space over F, where for these cosets V1 plus W and V2 plus W in V by W, and the scalar alpha in F, number 1 is just the addition we have in V by W, V1 plus, okay, let me just refill this. V1 plus W plus V2 plus W is equal to V1 plus V2 plus W. So this is nothing but the binary operation in the group V by W that we already know from group theory, where when we discussed quotient groups, there itself we define this binary operation. The second one is the one we have defined today, in this vector space. Alpha times V1 plus W is equal to alpha V1 plus W. Okay, so with these two operations, V by W is a vector space over F, and it has a name. This is called the quotient space of V by W. Then there are appropriate versions of homomorphism, isomorphism theorems for vector spaces, like how we had the things in case of groups and rings. If T is a homomorphism, okay, but before that let us just mention, let U and V be vector spaces over some common field F. If T is a homomorphism of U onto V, U onto V with kernel W, then V is isomorphic to the quotient U by W. Conversely, if U is a vector space, over F, that thing is there in the background, the field of scalars, and W is a subspace of U, then there is a homomorphism. Of U onto U by W, the natural onto homomorphism. Although the proof is really similar to the proofs of the similar results, corresponding results we saw in group set and rings, but still, for the sake of completeness, let us see the proof. Okay, and especially since the things are here, given together here. Okay, so first of all, it's given that T is a homomorphism of U onto V with kernel W. Then V is isomorphic to U by W. The strategy will be just what we previously had. So we are going to define, so the situation is like this. We have the vector space U, we have the vector space V, and we also have the quotient space U by W. Okay, we want to show that this is isomorphic to this. So what we do, we define a mapping from U by W to V. But of course, with the help of what we already have, here between these two things. Actually, we don't have anything in this direction, we have it in this direction, but for that I think it will be better to prove the converse first, because in the converse we have to show that there is a homomorphism of U onto U by W. It is that homomorphism. So let us prove the converse first. Define a map psi from, or let's just reserve psi for that other thing, let us call it phi, from U to U by W by U phi equal to U plus W. So the vector small u from capital U is mapped onto the quotient U plus W here. So we are in fact getting an element here. So it's a mapping from this to this set, and also clearly the mapping is well defined, because in the domain there is no coset involved, only in the only the output values are cosets, the inputs are not cosets. Clearly phi is well defined. Okay, so that is the first thing. Now we have to prove two things. Phi is onto and phi is a homomorphism. Ontoness is almost obvious. You choose any coset from here, any coset of W in U, that coset is going to look like this, where here you will have some vector from U. So that vector will be mapped onto that coset. So we are just simply going to write clearly phi is well defined and onto. Okay, next let U and V belong to U. Then phi is a homomorphism. I should not forget that we are in a vector space. So homomorphism needs to respect two different operations: addition of vectors and multiplication of a vector by a scalar. So instead of just taking vectors, let us also take a scalar. Then U plus V phi by our definition is this, which by the definition of the binary operation in U by W is this. And that again by the definition of the function phi is U phi plus V phi, and alpha U phi is equal to alpha U plus W, which is equal to alpha times U plus W, so that is equal to alpha times U phi. Thus phi is a homomorphism. So that's it. That's what we wanted to show, that there is a homomorphism from U onto U by W. Phi is such a homomorphism. Okay. Next, we are going to prove the direct part. This is the converse part. So in this case, okay, now again we come back to that situation. We have U, we have V, and we have U by W, where now we should not forget what W is actually. There W is not just any subspace. It's given that there is a homomorphism T from U onto V. W is the kernel of that homomorphism. But then W becomes a subspace. Now here we have that phi, and we want to define a map like this. So a map like this, or from that side to this side. Okay, let me just first try from this side. So from this side, if we start, then our input will look like this, some U plus W in U by W. Okay, that will be mapped onto UT. Okay, that will be mapped onto UT. Does it make sense? We start from here, so this is a coset coming from here, which is an element in this quotient space. So that means u is an element in capital U. Now on U, if we apply the homomorphism T, we are going to get an element in V. So at least our input and output are falling in the right sets. Then of course the question of this mapping being or not being well defined comes. So let us proceed like this. Next, define a map psi from U by W to V by this rule. Note that for any U plus W belonging to U by W, this is U, okay. U belongs to U and hence UT belongs to V. So our output does fall in V. Now next, let U plus W comma V plus W belong to U by W such that they are equal. We have to prove that their psi images are also equal, because then only psi will be well defined. Then two cosets are equal, so U minus V should belong to W. Now what is W? W is the kernel of T. So since U minus V belongs to W, so the T image of U minus V will be equal to the 0 element in V. Since this is the kernel of T, we have U minus V T equal to 0. But then UT is, in fact let's just write it, let's write the final thing. U plus W psi is equal to UT by definition. Now in place of U we can write V plus U minus V. Since T is a homomorphism, so T respects addition, so this becomes Vt plus U minus Vt. But this is 0, so this is equal to Vt, and Vt is nothing but V plus W psi. So having assumed that the elements are equal, their psi images are also equal. This proves that psi is well defined. So psi is well defined. Next, we are going to show that psi is a homomorphism. Let u1 plus t and u2 plus, no sorry, what, it's not t, u1 plus w and u2 plus w belong to u by w and alpha be a scalar. Then u1 plus w plus u2 plus w psi is equal to this. First we calculate the sum of the cosets in the quotient group u by w, and then on this we apply psi, which by definition is u1 plus u2 t. Now u1 and u2 are vectors in capital U, and t is a homomorphism from capital U into capital V, onto actually. So t will respect addition, so u1t plus u2t, but this is equal to u1 plus w psi plus u2 plus w psi. So psi does respect addition. Now let us see whether it respects scalar multiplication, or I should not say scalar multiplication, multiplication by a scalar, because scalar multiplication sometimes also means dot product, which is an entirely different thing. This and alpha times u1 plus w psi is equal to alpha u1 plus w. Keep in mind that every step of these calculations, when we are writing these steps, the justifications should naturally come to our mind. If that is not the case, then we will get lost in these abstract symbols. If we lose track of what we are doing, then it's game over. Okay, so now I am going to apply the definition of this function. So this is alpha u1 t, but again, because t respects multiplication by scalar and u1 is a vector in capital U, so this will be equal to alpha times u1 t. And that is equal to alpha times u1 plus w psi. So now we can say psi is a homomorphism. So psi is a homomorphism. What is the kernel of psi? We should not forget that psi is fine, psi is a homomorphism, but the domain of psi is u by w. So the kernel will contain cosets in it. So let say u plus w be any element in the kernel of psi. Then the psi image of u plus w will be the zero element where in V. So in V the zero element is just 0, so this is equal to and that is equal to ut. So we see that the zero the t image of the vector u in capital U is equal to 0. So this small u must belong to the kernel of T, which implies u belongs to W, because W is the kernel of T. Hence u plus W is equal to W. So this arbitrary element in the kernel of psi has been shown to be actually the zero element, because in the quotient space U by W, the zero element, the zero vector is W. Thus the kernel of psi consists of only the zero element or only the zero vector W in U by W. This proves that psi is 1-to-1. So psi has now become an isomorphism, a 1-to-1 homomorphism. Finally, we are now going to show that psi is also onto. Next, let V be any element in V. Since the map T from U to V is onto, there exists some vector U belonging to U such that V is the T image of U. But then U plus W belongs to U by W such that V is the psi image of U plus W. So we have found an element U plus W in the domain of psi, whose psi image is this chosen element V from V. So that just proves that psi is onto. Psi is onto. Hence psi is an isomorphism of U by W onto V, and hence V is isomorphic to u by w. So you see that the same things happen in groups, rings, as well as vector spaces. What is that thing? The thing is that there is a one-to-one correspondence between homomorphic images of a group and its normal subgroups. Like that, there is a one-to-one correspondence between the homomorphic images of a ring and its ideals. Now the result we have proved just now shows that there is a one-to-one correspondence between the homomorphic images of a vector space and its subspaces. One may question why this similarity. To see exactly why such similar results appear, you have to go to that area of mathematics known as category theory. Okay, where instead of studying a single group or a single ring, we consider the category of all groups, category of all rings, and not just algebraic structures, category of all metric spaces, topological spaces, differentiable manifolds, things like that. I want to study this part. I don't know I don't know anything about this area. So we will, if time permits, at one point we will study. This area actually shows us amazing relationships between different kinds of structures. For example, we will see at one point when we study algebraic topology how the category of topological spaces is linked with the category of groups. Okay, so this thing is over. Then again a definition. Let V be a vector space over F. And let u1, u2, etc. up to un be subspaces of V. V is said to be the internal direct sum of these subspaces if every element V belonging to V can be written in only one way as this. Where ui belongs to ui for so we have a vector space V and we have some subspaces of V, finite in number. In this definition, we say that the vector space is the internal direct sum of these subspaces if, first of all, every vector in V can be written as a sum of vectors from these subspaces. U1 is coming from U1, U2 is coming from U2, and so on. Un is coming from Un. And the second condition is that this expression is unique. So you should not have another sum where the components are coming, the summands are coming from these subspaces, and that is different from these things, okay, in at least some place, and that is also equal to V. That should not happen. This expression of V as a sum of vectors from these subspaces is unique. If this happens for every vector in capital V, then capital V is said to be the internal direct sum of these subspaces. A corresponding notion is the notion of external direct sum. Given any finite number of vector spaces, V1, V2, etc. up to Vn over some common field F. Consider the set V equal to the Cartesian product of these sets, which you already know what it is. It is the set of all ordered n tuples of vectors where the ith vector is coming from the space Vi. Okay, so this is a set we have formed from these vector spaces. Now one can turn this Cartesian product itself into a vector space over F in a pretty straightforward manner. All one has to do is define addition and multiplication by scalar component wise. And in fact, let's just do that. It is, should I write it here itself, or let me just first define the operations, then I will mention it. Because we have defined V as a Cartesian product, we already know when two such n tuples are equal, namely when their corresponding components are equal. By that we just simply mean this. Say you have one n tuple U1, U2, etc. up to Un, and you have another such, then they are equal if and only if the ith components are equal for all I varying from 1 to n. So all these things are already there in the definition of the Cartesian product. Okay, now we are going to define the operations for and V1, V2, etc. Vn in V we define their sum. First of all, number 1 when you hear something like this component wise and tuples are involved, ordered sets, you have to just understand that whatever we are going to do, we are going to do it to the components separately. So here the definition is u1 plus v1, u2 plus v2, and so on. This it's like handling these vector spaces, all of them together, but not mixing them up, handling them separately but doing all of that work together at once. And number 2 also similarly, alpha times. So note one thing before we define the second operation. This plus is the addition of vectors in V1. This is the addition of vectors in V2. This is the addition of vectors in Vn. Because the vector spaces can be any kind of spaces, so these operations may be very different from one another. Although we are denoting all of them by plus, but they may be very different from one another. The same thing it can be said for this multiplication by scalars. This is defined to be similarly alpha u1, alpha u2. So the meaning of alpha u1 may be very different from the meaning of alpha u2 depending on what u1 and u2 are actually. Then we mention it is a routine matter to verify that V is a vector space over F under the operations defined in 1 and 2, and this vector space has a name. We call V the external direct sum. It can be verified means at least superficially you in your mind you verify the axioms. Okay, first you have to show that with respect to this addition P is an abelian group, and then you have to verify the other 4 axioms. External direct sum of these spaces, and we express this fact by writing like this. when you see these classes, these circled classes, then you should understand that its external direct sum. Now naturally, because these two notions appear one after another, there is a relationship between them. That is the next theorem, which we won't prove in this video. We will prove it in the next part, but at least let's just state the theorem. If the vector space V is the internal direct sum, there is a corresponding concept in group theory, namely direct product. There are also internal and external direct product, but we have not got to that part yet. When we get to that part, you will see that the internal direct sum, because after all a vector space is also a group, as a group it matches with what we have in group theory. Okay, this definition matches with that one. Anyway, is the internal direct sum of the subspaces, say u1, u2, etc. up to un, then V is isomorphic to the external direct sum of this same, because the subspaces after all individually can be considered as vector spaces. They are of, so their external direct sum can also be formed. This theorem says that external direct sum is isomorphic to V. And once we prove this result, we will then do not distinguish between internal and external. These adjectives will then be dropped. We will just simply say direct sum. But we will be able to do that only after proving this result, which we will do in the next part. So I end the vector space video here itself. In the next part, besides proving this, because it's not going to be very long, we will start solving the exercise problems at the end of this section. So that will be all for tonight in vector spaces. So see you in the next part. Until that, it's me, Lucifer, from A Mathematical Room. Have a nice night.